All right, so today we're going to be covering 10.4, which is graphing rational functions. So let's talk about some of the vocabulary, some of the important things we need to know about this topic. A rational function is essentially when you take two functions and you divide them, two polynomial functions and divide them. And of course, we know that when we have something in the denominator, we have all types of restrictions, right? So those restrictions and those things that those denominators that remain act as asymptotes. Okay, we have horizontal and vertical asymptotes, and we're going to talk about how each of those can occur. You got to come up and get your notes, Anna. Okay. So zeros of rational functions occur at the values that make the numerator equal to 0. Vertical asymptotes occur at the values that make the denominator equal to 0. So these are some examples of what the asymptotes can look like. You can have more than one vertical asymptote as well, as you can see in the second photo, okay? All right, so best way to learn is to just start jumping in, but first we got to talk about how horizontal asymptotes come into play. So there's three different types of horizontal asymptotes that can occur. We have them based on how the function looks. So if a function is bottom heavy, the horizontal asymptote is always 0, y equals 0. Horizontal asymptotes are always y equals, vertical are always x equals, okay? So something is bottom heavy if the degree of the denominator is bigger than the degree of the numerator, okay? Something is has a coefficient of y equals the ratio if the degree of the top and bottom is the same. So do you see how the degree of the top and the bottom is the same because it's x and x? So you would divide the coefficients of x. So what's 6 divided by 4 going to reduce to?
3 over 2.
3 over 2. So in this case, for this particular scenario, it would be y equals 3 over 2 as our horizontal asymptote, okay, based on the coefficients. And then lastly, if something is top heavy, meaning the degree of the top is bigger than the degree of the bottom, this doesn't actually have a horizontal asymptote at all. This would have something what we call an oblique asymptote. And you may also see it written as a slant asymptote. Now in this class, we are not going to actually be finding these. You do this in calculus, sometimes pre-calculus as well. But you do need to understand like the concept of them existing. When something is top heavy, we know they exist, so it would have a slant asymptote. And they have to be found using long division. So let's just practice finding some points of discontinuity before we get into some of the graphs. So a POD, you'll see it abbreviated as POD, is a point of discontinuity. And the points of discontinuity can occur in two types, removable and non-removable. So removable discontinuity creates a hole in the function. So literally it looks like an open circle on the function, like a hole, like where we can't fill it in. So removable discontinuity occurs when you have two factors that cancel from the numerator denominator. So what factor is going to cancel out in this case here? X minus 2. So that means that we create a hole at whatever you removed, you're going to set equal to 0 and solve for x. So we know we have a hole at 2, comma something. We'll get to the comma part in a second. So just like you would have done before, remember how in the last lesson you would have said equals 0 to find where that discontinuity is? Same idea here. Now, once we remove that hole, or that factor, we're left with 1 over x plus 5. Does everybody understand why that is? That would be the simplified version of my rational function, okay? Now, we can use this simplified form to find the y-coordinate of the hole. So what you do is you take the function and you plug the hole into it, the x value, which would give you what y value?
7.
1 over 7. Does everybody see why it's 1 over 7? All right, so to find the other coordinate of the hole, you're going to plug that value back into the function. All right, so then we have something called non-removable discontinuity. This creates a vertical asymptote. So removable creates a hole, non-removable creates a vertical asymptote. The way I think about it is like a hole is like when something's removed, it leaves a hole, right? So that's how I remember which is which. So vertical asymptotes are basically vertical lines that cut through your function. They are called infinite discontinuity in higher math classes. In this particular case, is anything going to cancel out in this function? No. So because nothing cancels out, whatever remains in the denominator, you're going to set each of those factors equal to 0. Once you set each of those factors equal to 0, you're going to solve for x. those are what we would define as our vertical asymptotes. So that's how you find vertical asymptotes. Is everybody good with that? Are you ready to move on to an actual complete example? Okay. So the first example we are going to look at is going to be this function. Now, step one, before you get into any of these problems, first thing you want to check is, does this need to be factored? Would you say yes or no? No, it's already factored. Okay. So once you've identified if it's factored or not, you're going to look at it and see if it would be top heavy, bottom heavy, or equal. What do you guys think? Equal. So since it's equal, your horizontal asymptote, bless you, is going to be the ratio of the coefficients. So what would be the coefficient in front of the x? What would be the coefficient in front of this x? So what's 1 divided by 1? 1. So that's equal degree. Horizontal asymptote is y equals 1. And you can write, if you want, equal degree next to it to remind yourself where that came from. Okay? Now, next thing we're going to do is we're going to look at our function and see, is there any factors that I can cancel out of the top or bottom here? No. Like, you know how in the last one there was a factor that I could cancel out? There's none of those. So in this case, you see how a hole is created when something cancels out? We don't have a hole in this one, okay? Because nothing canceled out. Holes only occur when something cancels. So if you want to add that there so you know why. Now you know, it's because nothing cancels. So what you're then going to do is any remaining denominator after you cancel, of course we didn't have to cancel, you're going to set that remaining denominator equal to 0 to find your vertical asymptote. And then you're just going to solve for x. So we know that we have a vertical asymptote at x equals -2. So a vertical asymptote or a hole acts as a POD, a point of discontinuity. So we know that x cannot be what? -2. It's never going to be -2. And is that removable or non-removable? Did we cancel anything out? No, so we don't have anything removable, so this is non-removable. All right. Next thing we're going to do is the domain and the range. So, domain of the function is all the possible x values my function can ever take on. This function is continuous everywhere on x except for what values? What value? -2, right? X can be everything except for -2. Does everybody understand why that's the case? Okay. So my function domain can go from -∞ until it gets to -2. But -2 is not included in the interval, so we have to put a curved bracket. In addition to that, after, this is like where the asymptote is. So the asymptote's at -2. We're looking at the function on the left. The function picks back up after the asymptote, right? So we use the symbol called a union. And then the function picks up and goes from -2 to +∞. So this method of writing your domain is basically just showing that you're excluding -2 from that domain. It's everything on the left of -2 and everything on the right of -2. So the range is fairly similar. What's the only value in the range that your function is not going to be? 1 from the horizontal asymptote. So it's going to be the same idea. From below the asymptote, the function comes up from -∞ until it gets to 1. And then above the asymptote, it goes from 1 to +∞. And if this is like hard for you to understand, once we have the visual graph, I'll point it out to you like where that comes from, okay? All right, so before we can go ahead and graph it, we have to identify an x and a y-intercept if possible. So to find the x-intercept of your graph, you're simply going to set the numerator of your graph or your equation equal to 0 and solve for x. So we know we have an x-intercept at -4, 0. To find the y-intercept of your graph, you're going to take the equation after simplified and you're going to plug 0 in for x. Oh, I'm sorry. I see what you guys are saying. Yes, you are all correct. It should be a +4. Thank you. I don't know. I was just going with it too fast, you know. It's what you guys are for, checking my work. All right. So everybody good with my correction now with the x-intercept? And what would be the y-intercept? -2. Does everybody see why it's -2? Okay. So step 1 is you're going to plot the asymptotes first. So those are going to be vertical horizontal lines. So we have one at -2. And then we also have one at y equals 1. So this right here is going to act as like a barrier for your function, because your function is never going to touch these. It's going to curve around it. It's going to like get really close to it. It's going to be modeled by it, but it's not actually going to touch it. Next thing you're going to do is you're going to graph any holes you have as open circles, but do we have any holes to graph in this case? No. Next thing we're going to do is graph our x and y intercepts. So we have one at 4, 0 and 0, -2. Now that's all we know about the graph in terms of how we can graph it. So your knowledge of practice and understanding of what these graph looks like is going to determine how much or how little effort you're going to have to put into figuring out what this graph looks like. So theoretically, any type of graph in math, you can just plug x values in and get a y, right, to find out where the function is. So you may want to plug one in between these so we have a little bit of an idea, and then maybe one over here. So let's say we plugged in a -1. So I take my function, I plug -1 into it. I'm going to get -5 over 1, right, which is? So I know that my function has a point at -1, -5, which I can plot. So you might kind of start getting an idea of what this is going to look like. It's very, very similar to this type of shape right here, okay? So once you get the hang of it, you can just understand that this graph is going to curve around and toward the asymptote. It doesn't have to be perfect. Sure.
How did you find those two purple lines?
That is the asymptotes that we found earlier. So this one right here is the equation y equals 2. I'm sorry, y equals 1. And then the other one is x equals -2. You're welcome. All right, so now that you have your graph over here, you have part of it, we know that this graph is going to be in 2 portions. It's like split. So we know something exists over here. We don't know if it's below or above the intercept or the asymptote. So what you're going to have to do is plug a point in over here. So pick a number over here you want to plug into the function. Anyone? -6. All right, so we're going to take our function and we're going to plug in -6 for x. That's going to give me -10 over -4, which is positive 2.5. So at -6, my graph's at 2.5, about here. And if you plugged in a few other points, you'd start to see that it would curve this way. But like I said, I know that the graph is going to have symmetry, so I can just indicate that it's going to curve around the asymptote. The main thing you had to check a point for was if you wanted to know if it was going to be down here or up above here. But like I said, if you don't feel totally comfortable with guessing where the graph's going, what could you do to make yourself feel more comfortable and confident about graphing this? Just get more points. Okay, so just start plugging in. You could plug in -10, you could plug in -8, -6, and -4 to see what it looks like if you wanted to be more precise. All right, so now that we're here, as we go to the left, is my graph going down or up? It's going down, but it's going down really slowly, and it stops going down at what y value? Is it ever going to cross that asymptote? So it just approaches what? 1. It's not approaching any infinity because of the asymptote. It's always going to be approaching that asymptote. Now, I will be clear that some graphs can cross horizontal asymptotes, never vertical, but that's a whole other thing. But just treat it like it does. Over here, is my graph going up or down? Up, but is it ever going to cross this? No, so it's just at 1. So anytime your graph has this look where it's just getting closer and closer to those asymptotes, you know it's just going to approach the asymptote on the left and the right. Okay. Let's go ahead and try another one. So we're going to do each type of these. We're going to do a top heavy, a bottom heavy, and a regular all together. So would you say this one is top heavy, bottom heavy, or equal degree? Top heavy. So that means there is no horizontal asymptote because it's top heavy. Now that we've identified that, we want to factor this as much as possible. So how is the numerator going to factor here? What are some factors of -3 that add up to?
2, -1.
Good. +3 and -1, right? All right. So now that we factored this as much as possible, we are going to identify if this will have any type of removable or non-removable discontinuity. So, will this have any removable discontinuity?
Yes.
Good. It does have a hole. Yes. And the hole exists at 1, comma. In order to find the y-coordinate of the hole, you take the simplified form of your function and you plug the x value of the hole into the function. So it's going to be y equals 4 is where your hole occurs. Now I like to do this right off the bat because I often will forget. So at 1, 4, I want you to put an open circle on your graph. That indicates that there's a hole in the graph. Because sometimes when you forget to graph the hole right off the bat, you're going to graph it and forget to put the hole there. And then it's easier to just leave it now and not have to erase anything. Okay, so we do have a hole. Now that we have our simplified version of our function, we're going to take a look at it. Bless you. So when vertical asymptotes occur, they occur because there's stuff left in the denominator after we simplify. Is there anything left in this denominator after we simplified? No, so there's no vertical asymptote either. So our POD, we only have one POD in this, one point of discontinuity, and its x cannot be what? 1. And that would be removable or non-removable? Removable. Because we took it out. Okay, so everything else, we're going to wait and see the graph, except for we got to do these. I forgot about these. So x-intercept, you set the numerator equal to 0. Since it's just there's no denominator, you set just the whole thing equal to 0. So x cannot be what? I'm sorry, x is -3. So -3, 0 is the x-intercept. The y-intercept, you're going to take the function and replace x with 0. So I have a y-intercept at what value? 3. +3. Yes. So 0, 3. So once you have both of those, you're going to plot them. So here we have one, and here. Now, if you look at this particular function that we have left after simplification, does this function look familiar to you all? What type of function is that? Isn't this just a function you'd graph in like 8th grade? It's just a linear function with a y-intercept of 3. So it's just up 1 over 1, right? The slope. So if you want to get more points on this one, you can just follow the linear slope pattern. And then you can just connect it. Just don't forget to make sure you don't fill in that hole. That's really important. The hole has to stay a hole. So we're going to like draw around it, like so. Okay. So what you'll notice is sometimes when the whole denominator goes away, you're going to be left with a linear function. That's totally fine. End behavior is going to be a little different on this one, though. On the left, what's the function doing? Approaching. Good. On the right, it's approaching. Good. So see how this graph was infinite bound and the other one was not? See how it looks a little bit different? Okay. We still have to identify domain and range. So, domain. This graph is existing everywhere on the x except for what value? For the x. So, exists everywhere except for 1. Y exists everywhere except for 4. So that's going to be our range. Okay? Any questions before we move on to the last example? Anyone need more time?
Can you explain why there's no vertical asymptote?
Sure. So the asymptotes only for vertical only occur when there's something remaining in that denominator after simplification. Okay. All right. So for the last one, is it top heavy, bottom heavy, or equal?
Bottom heavy.
Good. When it's bottom heavy, we have a horizontal asymptote at y equals 0. And that's just a rule. Like, there's no, like, there is a reason, but, you know, all you have to know is bottom heavy, y equals 0. Next thing you're going to do is factor this completely. So, can I go about factoring the denominator? What's it going to become? Good, x plus 5 and x plus 1. Now that we've determined that, we're going to look at our function and determine if anything is going to cancel out. What do you guys think? Yes, so we do have a whole. And we know the whole occurs at -1 comma. We don't know where yet, but we can take our simplified version of our function. Yeah, it's going to be, the whole is at what? No, because we take the new function, which is 1 over x plus 5, and we plug the whole in to the function for x, which gives me 1/4. So I know I have a whole at 1/4. I mean, -1/4, yes.
So wait, why does y equal 0?
That's just a rule if it's bottom heavy, meaning the degree of the bottom
Okay.
is higher than the degree of the top. Yes.
How do we know that x value is
Whatever you canceled out, you see how we canceled out the x plus 1? You set that equal to 0. So x plus 1 equals 0 would yield me -1. And then to find the y value, you plug whatever that x value is back into the function, the simplified function. Okay. So we have one point of discontinuity. We're going to have to be able to fit 2 on the line here. So we know we have 1 at x cannot be -1, but leave room because there's another one. Once you simplify this, is there still an existing denominator on this function?
Yes.
That existing denominator indicates to me that I have a vertical asymptote. So if you want to write underneath it, this is the one that's non-removable, if you want to try to like add that in. If I kind of wish I put 2 lines for that part, but I didn't. So that's non-removable. So that's also a point of discontinuity. That's something that x cannot be, is -5. Does everybody see the difference between removable versus non-removable? Removable gets removed. Vertical asymptotes is what stays behind. Okay? So we have one of each. We have one of each. So if you want to list them over the top, like to indicate which is which, you can do that. The removable one was the x equals -1, and then the non-removable was x equals -5. So that's which one was which. All right. So as for everything else, let's find the x-intercept. So we're going to take our original function, and we're going to set the numerator equal to 0. Or I'm sorry, our simplified version. Can I solve that?
No.
So what do you think that means about the x-intercept?
Is it 1?
We just don't have one. Which makes sense because our horizontal asymptote is y equals 0, which is just the, what axis?
X-axis.
The x-axis. So if the horizontal asymptote is at the x-axis, are we ever going to have a 0? No, because we're not touching the x-axis. So it's kind of a contradiction, right? All right, so to find our y-intercept, we're going to take our simplified function and we're going to plug in 0 for x, which gives me what value? 1/5, right? All right. So I'm going to go ahead and graph my vertical asymptote. And we're going to come back to do the rest of the stuff after we see the graph, because maybe it'll help you understand better where these things come from. Okay. Now that I have my asymptotes graphed, I'm going to go ahead and graph my intercept, the only one I know, which is at 0 1/5. So it's like barely up here. It's like pretty small. It's going to be hard to graph, but just do your
How
best.
did you find that?
How did I find that?
The 0, 1.
Oh, so to find any y-intercept in any function ever, you just plug in 0 for x. Yes.
Wait, since it's 1/5, would that not be a fraction?
Why is it what?
Why'd you graph it at 0, 5?
I didn't.
Look, no, that's the asymptote. 0, 5.
It's this point right here.
Oh, I see. Yeah, okay.
was like, wait, did I graph something else?
That's -5.
That's the asymptote. Yeah, that comes from this. That's from this right here. This is from this. Does that make more sense now?
Yes.
You're welcome. Now we're going to graph our hole. We have a hole at -1, 1/4, so like just barely higher than the point next to it. So that means that my graph's going to go something like this. And if you wanted to test more points, feel free to do that. Now that we have this side of the graph done, we don't know if the other half of the graph is going to mirror over here horizontally or diagonally. So what should we do to test that out? Plug in a point. What point would be a good one to plug in? You say -8? That'll work. So 1 over -8 plus 5, that's y equals -1/3, right? So we know we have a point at -8, -1/3. That test point is going to tell me that I know I'm below the y asymptote. Does everybody see that? I did a test point. I plugged a random point in on the left. So I know that the graph's going to be over here. So the test point just tells me which way my graph's going. If it's going to be above or below the asymptote. That's really all it does. And like I said, when you do this on your own, if you want to come up with more points to verify that, feel free to do so. All right, so domain and range are going to be a little trickier on this one, so I want to make sure we talk about it. For domain, what are the two values that x cannot be? -5 and -1. So from -infinity to -5, we're good to go, right? But then at -5, we got to stop, and we got to pick back up after the asymptote. But then when we keep going from the asymptote, we got to stop at what value? -1, because we have a hole. But then after the hole, we can pick back up and just go off to infinity because there's no more limitations on the graph. Now the range is going to be a similar concept. -infinity until we get to the horizontal asymptote. And then from there, we go from the horizontal asymptote until we get to the y-coordinate of the hole. And then from the y-coordinate of the hole to positive infinity. So all of these U's, union symbols, basically represent where we have to break the graph off and pick back up. So you see how here, these are breaks in the x, and then here would be a break in the y, like that. So that's where those values come from. Now lastly, end behavior. Both sides of the function are approaching what value? 0. They're both getting closer and closer to the x-axis. Any questions about that? All right, I'll go ahead and hand out your homework, and you have about 20 minutes to work on it.